So this is on page 35 of your unit handout. We're dealing today with lesson 3.9, which is mechanical energy. Just a quick note about your Hooke's Law lab. Many of you have discovered your line is pretty straight. The proportionality is quite obvious when you look at your graph comparing the force to the displacement. Remember that I want that lab report in by Monday. If you were absent yesterday, there's a link in Google Classroom to the instruction of the lab and what's expected for the lab. As well, if you were absent, there's an email in your inbox of hypothetical data that you need to use to do your lab. So in the meantime, we're moving on here and looking at today at mechanical energy. We're going to be applying the idea of mechanical energy and the law of conservation of mechanical energy to solve some physics problems. To begin with, mechanical energy is defined a very specific way. And some of you might have a misconception about mechanical energy based on what you think the word mechanical means. But in physics, what mechanical energy is simply the sum at any point in time of all of the forms of energy that are kinetic and potential. So, for example, if I take a pendulum and I let the pendulum go back and forth, at some points in time, mainly at the bottom of the swing, the pendulum is moving quite fast. At other points in time, when it gets to the top of its swing, it slows down. It has to slow down because at the top of the swing it stops. So what I'm saying is if we could take a snapshot and freeze time when it's here, at this point in time, this pendulum has kinetic energy. There's a mass, and it's moving. And it also has gravitational potential energy because it's above its lowest point. And if I calculated 1/2 mv squared and mgh and added them together, that would be the mechanical energy. If I wanted to know the mechanical energy it has at the bottom, then I would take a mental snapshot of it at the bottom, and I would say, well, it's moving, so it has kinetic energy. I could calculate 1/2 mv squared. But for a pendulum, and we'll talk more about this later, I would say there's no gravitational potential energy at the bottom because it's at its lowest point. So even though it might be above the floor, we tend to use the lowest point as being no potential energy. This word, or this Greek letter, I don't know if I put this in your notes or not, but it's a Greek letter sigma. It's a capital sigma. And what it means in science and math is total or sum. And the reason why I've got sum here, it isn't really important for the kinetic energy because there's one type of kinetic energy. But I could conceivably have different types of potential energy in a system, so I would have to add them all up. The bottom line is it's the sum of all of the potential and kinetic energy. But the most important aspect, and I don't know that this is in your notes right here, at a certain point in time, would you agree that for this pendulum, let me get rid of this, would you agree that for this pendulum, when it's in motion, that when it reaches the highest point, which is right here, it has no kinetic energy? But would you agree that when it's at its highest point, right here, that it has potential energy? Okay. So if I wanted to find the mechanical energy of this pendulum here, I would take nothing for the kinetic plus mgh for the potential. Are you with me? Would you agree that at the lowest point, right here, well, here, it has no potential energy, but it has kinetic energy? So the mechanical energy at the bottom would be just 1/2 mv squared. Are you with me? I don't want anybody to think that because I'm saying mechanical energy is the sum of those energies, that the mechanical energy will be this potential energy at the highest point plus this kinetic at the lowest point. That's not it. The mechanical energy is this potential energy at the highest point, period. Or the mechanical energy is this kinetic energy at the lowest point, or the mechanical energy is a sum of the two at any other point. So what's missing in this definition right here is at a certain position or at one point in time. I think 99.5% of my students over the years would never even have to say that. It's obvious that that's what we're talking about. But every now and then I get a student or two that wants to add the kinetic energy at one point to the potential at another and say that's the mechanical energy. And in case it's not clear where the mechanical energy is in this pendulum, where the mechanical energy is in this pendulum in terms of kinetic and potential changes as it moves around. Now, quick question for you. If this pendulum rises to the same height that I dropped it from, which essentially it does, that means the mechanical energy it has at this point when I let it go is equal to the mechanical energy it has at this point when it returns, which means the mechanical energy stays the same everywhere throughout this pendulum motion. And what that also means is that if I drop this from here, it can't hit me. It can't get more energy out of the system than I start with. So although it seems a little scary, and I'm going to get a couple of you to try this, it doesn't quite touch me, which means that it does lose some energy. I'm jumping all over the place here, but why does this pendulum lose some of its energy? Who can tell me? And I have faith in physics, right? I know it's not going to clip me on the chin, but I still kind of flinch when it gets here. Jay? Right. There's friction with the air. There's also friction on the pivot point of the rope on the ceiling. I want to add something to that, though. Friction is not a form of energy. Friction is a force. What form of energy does friction produce? Heat. So the reason why it loses a little bit of its mechanical energy, a little bit, is because there are some forces of friction involved, and those forces of friction generate heat, which is a type of energy, and that means that some of the mechanical energy in the system is lost to heat. Heat is not included in this. Right? So if you have a pendulum and this is the highest point, then the mechanical energy at this point is simply the potential energy of the pendulum because it's at its highest point. If I look at it at the lowest point, the mechanical energy at the bottom is simply going to be its kinetic energy that it has at the bottom, because at the bottom it has no potential energy. Are you guys with me on this? What can you tell me? Look at the title of this lesson. It's mechanical energy, and we said we're going to be looking at the law of conservation of mechanical energy. Conservation of something means the amount you have to begin with is the amount later. So if mechanical energy is conserved, which it's going to be in every example we look at today but one, what can you tell me about the potential energy this pendulum has at the top and the kinetic energy it has at the bottom?
It is equal in magnitude.
They're equal. And we don't actually need to use the word magnitude because energy is a scalar, right? It's not a vector. On the other hand, at, say, this point, what is the mechanical energy? Well, I don't know if you get my subtlety on how I wrote this, but look at how big the EP was written at the top and look at how big the EP is written here. There's less potential energy. But there's also less kinetic energy at that point than there is at the bottom. So what's happening is as the pendulum moves, the potential energy starts dropping from the maximum. The kinetic energy starts rising from zero. So that means that this highlighted potential energy at the top and this highlighted kinetic energy at the bottom and this highlighted sum of the two anywhere else in between are going to be the same number if mechanical energy is conserved. So if the forces of friction are negligible, which means we can neglect them, which means there's negligible heat loss. We know, well, by the way, is this pendulum still moving? It's going to move for a very long time because it's moving very slow, so there's not a lot of friction with the air. And it's not pivoting very much at the top, so there's very little friction there. This will go for a very long time. We've talked before about the fact that objects that move faster through air experience more frictional forces. That's why this, although will continue for a long time, you will be able to see, I mean, if I distract you for a while over here for 3 or 4 minutes and then come back, you will be able to see that it's nowhere near as close as it was to begin with, right? So there is a loss here. Finally, before we really get going on this, I hope you understand the need in science education for you to be taught how to do problems under ideal situations before we can worry about reality. This is why when you learn about your kinematics formulas, you go, well, let's neglect friction. Well, I'm sorry, when you drop a baseball 100 meters from the top of a building to the floor, there's friction, but we ignore it to learn better. Okay? All right. An isolated system is one in which no outside work is done to the object in the system. So wait, work is a transfer of energy. What an isolated system is a system in which the energy in the system is not changed because you don't transfer energy into the system or out of the system. In other words, an isolated system would be one where there's no friction. Because friction is going to take mechanical energy out of the system. So when friction acts, there is heat energy generated. So in an isolated system, there are no frictional forces present. When you get to physics 30, that definition of an isolated system becomes more sophisticated. There's more to it than that. In an isolated system, if there's no friction producing heat, then there's no heat loss. And if there's also no work done by anything else, like when I say no outside work is done, there's not an invisible monkey pushing this pendulum faster at some point in time. What that means is mechanical energy will be conserved. And this is what we're dealing with today in these examples. Quick question here. Well, mechanical energy can be transferred from one object to another or from one form to another, but it will not be increased or decreased. It's the law of the conservation of mechanical energy. Examples. What is the relationship between the potential and kinetic energy an object has when sliding from rest down a frictionless inclined plane? It's a pretty open-ended question. It's not really asking specifically for you to do something. But what the drive of this question is that EK plus EP will equal the same value anywhere on the ramp. That's one thing that we can say. Since it's frictionless, it's called an isolated system. Since it's an isolated system, no energy, mechanical energy, is added to or taken away from what's in there, and that means that mechanical energy is conserved. Another thing we could say is, don't forget, this is saying as the object is sliding from rest down the plane. As the object is sliding from rest down the plane, EP is converted to EK. and I want you to try to understand that it's not just that something magical happens, that there's potential energy at the top, and then when it gets to the bottom, all of that potential energy suddenly turns to kinetic. It's happening gradually. You know, and even this illustration I'm going to give you, I think it's next, is not, I mean, it's a series of snapshots in time. Here's the red box at the top of the ramp, and it's just being held there, being ready to be released. So all of the energy in the system is potential, and there's no kinetic. If I let it slide down and I take a snapshot at some later point in time, it will have less potential and it will have more kinetic. I hope you understand, and if you're watching this on video, you can't see this action. But it doesn't go blink like that. It does this. Right? It's a gradual thing. But I didn't feel like making some kind of flash animation or anything here. I just did a cheapo, cartoonish, like a flip book. Remember those flip books? And eventually what happens is, by the time you get to the bottom, look at the level of kinetic energy in the system at the bottom. And if I go back and look at the potential energy it had at the top, whoops, it's the same. So if I were to put a scale on this and I said that this is 10 joules, and I looked here, I just want to check something out. If this is 12 joules of potential, then at this point in time, we have 10 joules of potential and 2 joules of kinetic. At this point in time, we might have 4 joules of kinetic and 8 joules. At this point, we might have 6 joules and 6, well, see, I chose, the scale is wrong here, right? You can see that those numbers are not matching up. I would have to rethink the numbers. But the bottom line is the total energy at any point in time has to be the same. Okay, let's take a look at the next question. Number 2. What do we have? We have a frictionless roller coaster car, which is a dream. Can't get purely frictionless, but it's close, actually, particularly when the car is moving downhill. Has a mass of 800 kilograms. At one point in its journey, the car is moving at 4 meters per second and is 35 meters above the ground. Some later point in time, it's moving at 20 meters per second. What is the initial total mechanical energy relative to the ground? Well, mechanical energy is equal to mgh plus 1/2 mv squared. Right? That's what mechanical energy is. Potential energy plus kinetic, and the potential is gravitational. Can I cancel those masses? No. That'd be like saying, find the weight of an object, which is mg, and you go, well, I'm going to cancel the mass. You can't do that. You could cancel them if this was equal to something else that had a mass, but we're just trying to calculate mechanical energy. So I'm going to take 800 kilograms. I'm going to leave the units out today for this, times 9.81 newtons per kilogram, times the height of 35 meters. And we need to add 1/2 times the mass, which is 800, times the speed, which is 4 squared. Let's calculate both of these separately for me, please. I think it's 6,400 joules of kinetic. I can't be that fancy in my head with this other stuff. 35 times 9.81 multiplied by 800. 274,680. You getting the same number before I continue? Okay. So we need to add these two together. to get the mechanical energy of 281,080, but I did that in my head and I could have carried wrong, but is that right? Okay. That's the total energy in the system. Most of it is potential. Some of it is kinetic. But that's the answer to A. What is its gravitational potential energy later on? Okay, so you read that, just a second here. You read that and you go, well, that's mgh, but we don't know the height later on. However, we know that at one point in time, the mechanical energy is 281,080 joules, I think. Yes? And at some other point in time, its mechanical energy is 281,080 joules. Because there's no friction. If there's no friction as a force, there's no heat as a form of lost energy, which means mechanical energy is conserved. Well, this has to be equal to, pardon me, that's 281, right? This has to be equal to this 281,080, the potential energy it has plus the kinetic energy it has. It's just at a different place now. This is the place where it's moving at 4 meters per second and has a height of 35 meters. This is the place where it's moving at 20 meters per second. I mean, you don't need to think this way, but how many of you realize what's happened is the height has decreased? Because 20 meters per second is faster than 4 meters per second. Of that 281,080 joules, more of that energy is kinetic now, which means less of it is potential, which means it's at a lower height. Let's calculate the kinetic energy here. It's 1/2 times the mass, which is 800 rather, times the speed squared. The kinetic energy in the second instance, and that's when I say it's a trivial calculation, I mean it's just a simple calculation. We should have no problems with that. I want to say it's 160,000. So what we have then is 281,080 as the total mechanical energy in the system. The potential energy we want to find, the kinetic is 160,000. It's a pretty straightforward thing to, I'm missing a 0 there. It's a pretty straightforward thing to subtract that 160,000 mathematically from both sides and get 21,080. So EP is 21,000. Can you read off the digits, please? 121,080. Thank you. It's off by a decimal there. So that's the answer to the question. But again, I want to point something out to you. At the top, at point 1, this is the distribution of potential and kinetic energies. At point 2, this is the distribution of potential and kinetic. So when you compare the potential energy to begin with to afterwards, it's dropped by an amount. When you look at the kinetic to begin with to afterwards, it's risen by an amount. And I hope it's obvious, but I'll say it anyway. Whatever amount the potential energy dropped by, the kinetic energy increased by. Because if the sum of those two have to be the same, you can't have one losing more energy than the other gains, or vice versa. So this is the answer to our question. By the way, you could determine the height now. You could set that energy equal to mgh. Number 3, an ideal pendulum. Ideal means no friction. An ideal pendulum is suspended by a string that is 2 meters long. It is pulled sideways and released. At the highest point of the swing, it is 25 centimeters above the floor. At the lowest point, it is 5 centimeters above the floor. And you're given the mass. What is the mechanical energy of the pendulum relative to the floor? Okay, so first of all, this will probably be the only time in the course where we will ever do that. We're going to see examples where it's easier to use relative to the lowest point. And the reason for that is, if I get my pendulum going again, if I use the floor as a reference point, then at the lowest point, there's potential energy because it's above the floor. But if I use the lowest point as the reference point, then at the bottom, there's no potential energy because it's at its lowest point. However, we are asked relative to the floor. Mechanical energy is total EP and EK at a single place. This pendulum is raised to a height of 25 centimeters above the floor. I'm not going to stoop down. Let's just imagine this is 25 centimeters above the floor. And it's going to be released from that point. Are you with me? What kind of energy does it have at this point in time? Potential? mgh? Does it have any kinetic here? No. So if you calculate the potential energy at the highest point, you will have found the mechanical energy. On the other hand, had I told you that at the lowest point it has a particular speed, that you could find the energy there. But at the top of the swing, there is only potential energy. So the mechanical energy at the top, the mechanical energy at the top, which since it's an ideal pendulum, is the mechanical energy in the system, anywhere, is simply going to be mgh. So the mass is 0.25 kilograms. I'm going to abbreviate G. We know what G is, 9.81 newtons per kilogram. And 25 centimeters above the floor is 0.25. Gives me 0.613125 joules. I'm just going to record all of those. What is the mechanical energy of the pendulum relative to the floor when it's at the lowest point? Who can tell me the answer to that question? It's the same number, right? It's not asking you to do anything beyond that. I'm really just, with these introductory examples and warm-up questions, I'm trying to get used to the fact that you need to pay attention to words like mechanical or kinetic or potential. Mechanical means anywhere the sum of potential and kinetic. And if it's an isolated system, it will be the same everywhere. What is the kinetic energy when it's at the lowest point?
0.613.25.
No. The kinetic energy at the lowest point is not that same number. Why not?
Because it's not actually on the floor. That's not below.
Right, because we were forced to use a reference point of the floor at the lowest point. There is potential and kinetic. And this has to equal the 0.613125 joules. What we are asked to do is find this. We want to know how much kinetic energy it has at the bottom. So what we need to do, I suppose, let me just give myself a little bit more room here. What we need to do is calculate this. This will be the mass, 0.25 kilograms, times g, which is 9.81 newtons per kilogram, times 0.05, 5 centimeters. Are you starting to see why it's not the wisest choice to use the floor? Because if we didn't, whatever number we got, which is the one you're probably looking at right now, would be the answer to this question. Whatever number we got for the previous question would be the answer to this one. So what does this work out to? This works out to 0.25 times 9.81 times 0.05, 0.122625. So 0.1222625 joules is the potential energy at the lowest point, plus the kinetic energy at the lowest point, which we're trying to find, is equal to the sum of the two, the mechanical energy at the lowest point, because the mechanical energy that we calculated at the highest point is the mechanical energy at the lowest point. So all we have to do is subtract these two now and get an answer. And my brain, left side of my brain, just looked at the right side of my brain and said, let's take a nap. So I'm going to use my calculator. I need to take 0.613.125 and subtract that, 0.4905. So the answer to this question is 0.4905 joules. And I'm carrying all my decimals. You know, on an exam you would round. Let's pause for a second there. Let's not do D. Let's just ask ourselves, if we had this situation where here's the pendulum at the lowest point, here's the pendulum at the lowest point, and that happens to be 5 centimeters above the floor, but we decided, here's the floor, this is 5 centimeters, this is 25 centimeters. If we decided to use the lowest point as the reference point, then this distance would be 0.2 meters. Can you just mull that over? And if I said to you, we go back and look at A, and I said, what is the potential energy or mechanical energy relative to the lowest point, you would say, since the pendulum is 20 centimeters above the lowest point, we'll do an MGH calculation with that. So your answer to question A would have been this. It would have been 0.25 times 9.81 times 0.2. Are you with me? Wow. Imaginary numbers. We don't want those. 0.25 times 9.81 times 0.2. Are you with me? So the answer to A would have been 0.4905 joules. And B, what is the mechanical energy at the lowest point? Would have been 0.4905. And C, what is the kinetic energy at the lowest point? 0.4905. And that would mean we don't have to mess about with all this stuff. And particularly when D is the answer to the question that we really are after. The question would normally be, I drop the pendulum from this location, how fast is it moving at the bottom? So we can take the kinetic energy at the lowest point, which is 0.4905 joules, and set it equal to a half mv squared. And whether we get it by, I'm not sure what happened there, by going through this whole process or being clever about it and using the lowest point as 0, doesn't matter. So now we've got 0.4905 equals 1/2 times the mass, which is 0.25, times v squared. And again, just before we get a number here, all this A, B, C, D is just kind of nonsense because the question would be given on an exam, how fast is it moving at the bottom? I have to multiply that number by 2 and then divide it by 0.25. So multiplied by 2 divided by 0.25. You're going to get a speed very close to 2 meters per second, are you not? 1 point, well, let's just say 2.0 meters per second. And now what we're going to do is start putting this all together so that we don't have to go A, B, C, D. 10 kilogram mass slides down the frictionless ramp from the top. What is the speed of the mass at the bottom? Well, let's see. Mechanical energy at the top is equal to mechanical energy at the bottom. Somebody want to let us know why we can say that? Everybody think about that for a second. Why can we get away with saying, well, the mechanical energy is conserved? Jay? Right. There's no forces of friction. If there are no forces of friction, there is no heat generated. If there's no heat generated as a form of energy, the mechanical energy is the same. At the top of the ramp, there is only potential energy. At the bottom of the ramp, there is only kinetic energy. It's like a pendulum, but it's not attached to a string. I did not need to tell you the mass for you to answer this question because the masses cancel. We have a mass on each side. So we're not going to calculate the potential energy at the top and then use that to find the speed at the bottom. We've set up an equation. The only thing that's missing is the height of the ramp. It's a straight Pythagorean theorem. 8 squared will equal 6 squared plus the height squared. That h in my equation that I just wrote there is not hypotenuse, it's height. So 64 minus 36 is 28, the square root of 28. Is it 28 though? Okay. So h equals root 28. There's nothing wrong with you just putting root 28 in. Who's in math 20-1 right now? You guys are doing radicals by now, aren't you? So I mean, it's just that number on your calculator, that 5 point whatever, that's not root 28. That's a decimal approximation. So I'm going to carry all my decimals by just putting root 28 there. I need to take 9.81 times, well, you know what? Let's do this. Multiply both sides by 2. So now it just tells me I have to take 2 times 9.81 times that height, and then take the square root to get my answer. And I mean, I don't know what possessed me to talk about root 28. I guess at some point you have to figure out what the number is. Right? I just thought I would make a connection between physics and math. Because we don't want, in math, we don't want decimals, but in physics we do want decimals. We don't want to write roots as answers. So this is my height times 2 times 9.81. Don't forget to take the square root. It's moving at about 10 meters per second, 10.2 meters per second. You good? I don't know what that is. It's a little roller coaster car with a couple of blobby aliens in it. It says the roller coaster car passes the highest point with a speed of 15 meters per second. How fast will it be moving at this point? So we've talked about this a number of times, but you are allowed to use whatever reference point for MGH you want to. And we could use the ground, but if we use the ground, then there would be potential and kinetic at the top, and there would be potential and kinetic over here. We could use the lowest point as the reference point, but we would still have potential energy at the 33 meter mark. So the wise thing to do is to say we are going to use that height of 33 meters as being 0. We're making an assumption here that we can neglect friction because you can't do the question unless you assume that. At the top, we're going to have mgh plus 1/2 mv squared. At the bottom, we are going to have 1/2 mv squared. No potential at the bottom. By the way, you understand, I hope, when I say bottom, I mean this point at the 33 meter height. Okay. There's no potential there because we have cleverly said that's 0 for the height. I can cancel all of the masses, and I'm going to multiply both sides of this equation by 2. I guess since I have two v's, I'm going to say v initial and v final. Are you okay with that? So if I multiply both sides by 2, I get 2gh plus vi squared equals vf squared. Does that look familiar? It's kind of like a kinematics equation. It's not the kinematics equation, because the kinematics equation is vf squared equals vi squared plus 2ad. D is the distance traveled. It doesn't travel whatever that height is. That's not the distance traveled. It travels an angular distance or a curvy distance. And in the kinematics formula, it's not g, it's acceleration. The acceleration of this car is going to be changing all the time because of the forces involved. But it's very similar. So now we can just put the numbers in. However, we'd better talk about what you're going to use for h. H is the height above the lowest point. Well, that would be 40 minus 33, which is 7 meters. I can put the numbers in now. 2 times 9.81 times 7 plus 15 meters per second squared equals VF. By the way, this is a very efficient way to find answers to problems using conservation of energy rather than forces. Did I write something down incorrectly?
Wouldn't the VF still have the square?
I forgot to write the squared there. Thank you. Yes, equals VF squared. What are we going to get here? 2 times 9.81 times 7. Thank you. 2 times 9.81. Gave me a break today, actually told me. Times 7 plus 15 squared. Look good? Equals, take the square root. So the answer to the question is it is moving at 19 meters per second at that point. Now, it would have been moving faster at that lower point, but we don't need to worry about that. In other words, since mechanical energy is the same everywhere, it doesn't matter whether it gets to this 33-meter mark this way or that way. It doesn't matter because the energy is the same everywhere. I'm going to end. Well, no, let's do this one. It's not going to be a lengthy thing. Let's do it. Number 6, this is the final example, I believe, correct? Okay. A 12-kilogram mass slides down the ramp from the top as shown. It reaches a speed of 6 meters per second at the bottom. What's the potential energy at the top? So, little math exercise for you to begin with. Since potential energy is mgh, you need to find the height. Let's do a trig calculation to find the height. I believe it's going to be 3.75. So this is just mgh. It's 12 times g times 3.75. I left out the units. I abbreviated g. I just don't have a lot of room here right now. So we got 12 times 9.81 times 3.75, 441.45 joules. Are we okay with that? Okay. What's the kinetic energy at the bottom? No. It doesn't say it's frictionless. But you are given the speed. So how are we going to find the kinetic energy at the bottom if it's not frictionless? Yeah. But the only way that would work, Jay, is if we knew how much heat was produced, if there's friction, and we don't. And I think maybe you might be one step ahead of me. Right now, we're just interested in how much kinetic energy is at the bottom. Let me ask you a question. If there were no friction, what would the answer to question B be? Be that 441.45. Could the answer to question B ever be more than that number? No, not unless somebody's pushing. But we don't even know the force of friction. And by the way, we can't find it. Well, we can. We'll get to it later. But we can't find the force of friction until we find this energy. And by the way, we would never subtract forces and energies. They're different things. So I'll ask the question again. How can we find the kinetic energy at the bottom? Declan? 1/2 mv squared. We're told how fast it's moving at the bottom, and we know the mass, so let's find the kinetic energy at the bottom. So sometimes, and there's a lesson to be learned from this little discussion, sometimes you get so caught up in the big picture, oh, mechanical energy is conserved, you forget to read the whole question and look at what information you have. So at the bottom, the kinetic energy is 1/2 mv squared. So this would be 1/2 times 12 kilograms times 6 squared, which is giving me 216 joules, I think. Okay. So I'm going to ask a totally different question now. Somebody is asked, a student is asked, how much mechanical energy is there in the system? And the student adds these two numbers together. Why is that wrong? Give it a shot. Right, that's exactly the reason. That 441.45 joules is the potential energy at the top, and it's not moving at the top. So that means at the top, the mechanical energy is 441.45. That's the mechanical energy at the top. If I said to you, what is the mechanical energy at the bottom? At the bottom, it's all kinetic, so the mechanical energy at the bottom is this. In other words, asking a student, what is the mechanical energy in the system, is a bit of a trick question. It's a value that changes from 441.45 at the top, and the total mechanical energy bleeds out of the system to heat, leaving us with, at the end, 216. The question now is, what's going on? Well, there must be a force of friction. It's not an isolated system. If it's not isolated, that leads us to the conclusion that there is a force of friction present. That leads us to a conclusion that heat is created. And be very careful here. This is a force. This is an energy. These two things, the force of friction and the heat, are as different to each other as the color of a cheesecake and the flavor of a cheesecake. They're different things. Are they related? Yes, because if the color of the cheesecake is black, the flavor is probably going to be different because I overcooked it. Or because I got a licorice cheesecake, if such a thing exists. But the point is, the color of something and its flavor, although they may be related to each other, are as different as, chihuahuas and dollars. They're different things. Force is not energy. By the way, this question says, how much heat is lost by friction? Well, if you had 441 joules of energy in the system at the top, and you only have 216 at the bottom, whatever is the difference between them is the energy produced by friction. So 441.45 joules minus, you know what, I'm going to actually do this a different way. Let's find the, no, let's not. 441.45 joules minus the 216 joules. $225.45? Okay. So about 225 joules of heat. There's a way to find the force of friction, but I don't think it's important for today. Any questions with that final example? All right, so you can get to work on these problems. I would say the problems in your unit handout are sufficient. I don't think you need to do the textbook problems. Does anybody want to try this? You want to try it? Okay. It's best to put your head right against the back of the wall. Okay, so it's right on the chin. Now what I could do is, ask him to close his eyes, and then when he closes his eyes, when I drop it, I give a little forward push. But I won't do that. Okay, you hold it. You hold it and drop it. Put it right up to your chin, right up. See, there's a little. It's hard, and when you drop it, try to drop it like perfectly straight, so it's along the line of that bar, and it moves pretty quick. Let's face it, if you were laying on the floor and that clipped your chin when it hit you on the floor, it would leave a mark. Try it as well. You can bring it right up to your nose. And it's even if you do it 5 or 6 times, there's that flinch there. If you want to try it, help yourself. If not, let's get to work on these problems.